Yes.
So one aspect of Wi-Fi frequency and waves, we have a new standard 5 gigahertz, and there are new implementations of the 5 gigahertz bandwidth that include new Wi-Fi standards like Wi-Fi 6, Wi-Fi AC, and so that's all part of the 802.11 series of references provided by the IETF, the IEEE. We'll talk about that more in detail and probably do a deep dive on that in later modules. What you'll notice here, though, as we take up our class, what I'd like to do is revisit this notion of the battleship in the water, because I want to have a second crack at this with you to explain what's going on here. And everybody can see this clearly, yes?
Yeah.
Okay, so what we have is a large warship. We're going to pretend this is a battleship. And if you have Wi-Fi frequencies that are longer wavelengths, this is not unlike a large ocean wave. So if you have a large battleship out to sea and a large ocean wave passes through the area where a battleship is, the entire battleship rises and falls with that large ocean wave. The large ocean wave continues on as if the battleship were never there. And this is not unlike older versions of cellular service, older versions of Wi-Fi, which have longer wavelengths. Now, as you have probably experienced, on top of the larger sea waves are ripples, smaller waves with shorter wavelengths or greater frequency, right? Shorter wavelength means greater frequency. When these encounter a battleship, if they were running in this general direction, straight up the page, and they hit the battleship, what you notice behind the battleship is a wave shadow of sorts. It's completely calm behind that battleship for a short distance, not very long, but for a short distance. And all of the ripples are gone. Now the large wave continues, but the ripples are dampened or nullified or canceled by the physical structure of the battleship. This is not unlike your 5 gigahertz Wi-Fi signal, which in Wi-Fi terms will carry more data because there's more cycles per minute. There's more hertz or cycles per minute. So you can represent more ones and zeros. There's more bandwidth. And we've already explained that Nyquist, pioneer in Wi-Fi and radio research, had come up with a basic formula and stood on the shoulder of other giants, right? Like Fourier, who calculated how this modulation works, a wave embedded on a wave, right? This is one aspect of Wi-Fi that is important to understand, because when you have greater frequency, the distance and penetration capacity of that higher frequency is decreased. So the greater the frequency, the more data it can carry. But the greater the frequency, the more subject to interference and physical objects it becomes, okay? Now, given this information, is there anyone who can think of a decent question or would like to offer a comment based on the information we've just related? Maybe not so much, huh? All right, well, let's continue. Remember that much of standard Wi-Fi is located in the microwave frequency range. When we say microwave frequency, we're talking about 2.4 gigahertz. 2.4 gigahertz is also the same frequency for Bluetooth and some other forms of wireless and Wi-Fi. Let's get a snapshot. There we go. So let's continue on here with Wi-Fi, right? So when we talk about waves, whether it's wire or radio, you have a carrier wave and you have encoded data. We call this signals over media, right? And essentially, the rules of transmission to send and receive signals over media are distinctly different from those that manage the packets of binary data that flow on top of those signals. So that's something we want to call out when we start. We want you to understand that when we're talking about the network addresses and such, that's on a higher layer called the network layer. We're talking about layer 1 and layer 2, where the interface connects to the media. And there are signals that are received by that physical interface. And a transformation occurs between the signals that are running over the media and what happens when it hits the interface. So this is like a critical place, and it's also very physical. And we've already explained that essentially the physical layer is what plays hell too often for many technology professionals, right? Because they simply neglect the physical layer and they don't assess properly. They do some quick checks and they say, yeah, it's plugged in. Yes, it's running. Yes, I have what I'm supposed to, but realistically, whether they are truly checking the environment and the related logistics, the electrical, the ground, the interference in the vicinity and so on, you have, you basically have a case where a lot of disruption can occur, and then people are still scratching their heads after they've checked everything else. So always remember that it pays to go back and double check your physical layer, and especially with signals, right? When you have a physical breach or you have obstacles in the area, whether you're talking about Ethernet or you're talking about electromagnetic interference with fluorescent lights, or you're talking about physical break in the cable, anything that disrupts the signal is going to have a dramatic effect on the ability of transmission media to carry data. And when we're talking about protocols now, there is a formal aspect of protocols. So when it comes to the protocols that have been created to help manage and engineer signals over media, there's a difference between syntax and semantics, and that's something from module 1. So that's, I just want to call that out and explain. Okay, some of the stuff has to do with the actual transmission and send and receive. Others have to do with the meaning of a thing as it's received. So there's physical, logistical aspects of a signaling protocol, and then there's interpretation of the results on the other side that have to do with the meaning, right? Let's continue and explore the rest of carrier waves and encoded data. So we want you to be able to speak to this interest when we're finished our review here. Analog transmissions use all of the variations of the wave sent. And this is a review of what we shared in module 1. The same entire signal is fed back into a receiver to simply play back the content. But when we're talking about digital transmissions, the signals are interpreted and represent only 2 values, 1s and 0s. So analog transmissions and the receipt and interpretation of analog transmissions, old school, old methods, circuit switch networks. Those are incredibly complex, require amplification over a certain distance and so on. Digital transmission is much simpler. All we're doing is forming a signal pattern that represents ones and zeros. And these are clearly discernible even when the strength of the signal diminishes, right? So even when it's not very high, which is why digital, a proper strength of digital signal for FM radio is so much clearer. And maybe your parents or grandparents can talk about AM radio versus FM radio. But on a related note, if you have a digital FM signal for a radio station and you have old school analog AM radio, they would tell you that the volume and integrity of what's being communicated on the radio fades, but it gets weaker and weaker. You have to turn the volume up higher and higher and higher. With FM digital, when you're out of range, it just drops. So it's working and it's fine, or it's not, and it doesn't work at all, right? So that's one of the differences. That's one of the other manifestations of differences between analog signal and digital signal. So for transmission involving electromagnetic energy, one of the things that takes a little bit of time to wrap your head around is that radio waves, X-rays, ultraviolet, visible light, infrared, those are all different types of electromagnetic energy. And this is, so this is a phenomenon that's explored in the physical sciences. And it is part of the flow of electricity. Whenever and wherever you have electricity in motion, you can see that there is the generation of an electromagnetic wave. By the same token, you can move a conductor in electromagnetic fields and create electricity. This is the basis for alternators and generators, that you have magnets and they're rotating and there's motion, and it's in the presence of a conductor, and that moves electrons. And so the electrons start moving. One of the coolest things you can do to just get a feel for how potent this whole electromagnetic interest is, and you wonder, why do we have so many twists per inch with Cat5 cable and so on? Cat6 cable, there's even more. Cat7, there's even more. You can take 100-foot extension cord out into your front yard, and I would challenge you to do this. Take a 100-foot extension cord, if you have one in your hurricane kit, take it out into the front yard, ask a family member to hold the other end, and then what I want you to do is to play jump rope with it. So have a third member of your family jump rope as you swing it around and around. Now, a fourth member of your family is going to take a small, inexpensive voltmeter and stick it in the ends of the jump rope. And what you'll see is that there's electricity moving with each cycle of the rope. There's a pulse of electricity, and I'm not making that up. It's pretty dramatic to see when you do that. And it also nails home this notion that you have peaks and troughs, right? So when you have a certain frequency of the extension cord jump rope moving, you have a certain pulse of electricity on the voltmeter. And that sort of helps everybody physically to see this in person. It's kind of a connect the dots, the light bulb comes on, everybody goes, ah, okay. Now, one thing that is important to understand is that as this signal fluctuates, the height decreases over time. The term for this is called signal attenuation. And it may be of interest for you to know that when plugs and cables are fastened properly and then plugged into patch panels and wall jacks and patch cords are used to connect equipment, the interfaces between those connections actually help dampen the signal in a predictable manner. And this is quite useful when it comes to things like lightning storms. It is generally a bad idea to have a long Ethernet cord with two RJ45 plugs on either end and then connect two devices. First of all, you have to create what's called a crossover cable between those two devices. But the other problem is that when you do such a thing, if there's any electromagnetic energy in the area from lightning storm, it's going to generate a pulse of electricity and it'll fry both of those devices on either side, unless there's a surge protector in the mix. Okay? This is just one thing to understand. If you have the proper installation, solid core, stranded core, things we talked about previous class, what will happen is that lightning storms will roll through the area and occasional electromagnetic energy from different sources, like, a fluorescent light, won't be the end of the world, because that interference is also dampened or attenuated in a specific manner. So it's a fancy word, but we want you to understand why it's significant and how it helps. It actually helps in terms of the quality, maintaining and managing the quality of the signal for shorter distances. So even though the signal is lessened, it's cleaner and it's regulated, so to speak. I love this. If you haven't seen this here yet, this is really something that's cool. So this explores the two different kinds of modulation. When we're talking about signals over wire, we're talking about a carrier wave, and then there are other signals that are embedded on top of the carrier wave. So here you see AM and FM radio. And if you click on this, what you'll see is a graphical representation of the difference between AM and FM. And so digital information is more easily embedded on top of FM because of the consistency of the peaks and valleys, the amplitude of the waves. Where AM, the amplitude of the signal changes with the carrier wave. Can everybody see that?
Yeah.
Yeah, that's just cool. I mean, whoever did that used to explain this on a whiteboard, and it took about, I don't know, 4 or 5 minutes to get all that explained. And now you have one moving picture and everybody's. So this is also a very useful related website, and it talks about different forms of modulation. I would encourage you to review this at your leisure, but it also introduces other concepts that we will engage later on, like some of the different formats of digital modulation. QAM is one they use for cell phones quite a bit, right? So you'll see references to QAM when it comes to cellular wireless service and so on. Moving right along, there's actually a digital component. There are two digital components that are specifically relevant. We look at CSC 241, computer architecture. We talked about how there was something called a digital signal processor, and there's another component called a UART, a universal asynchronous receiver transmitter. And these two components in particular are embedded in the history of early internet, because we had this gadget called a modem. And modem was an abbreviation for the term modulation, demodulation, where ones and zeros were embedded on analog signals on plain old telephone lines. So they were modulated and then demodulated on the other side. And there was this hokey little squealy kind of thing that happens when they're connecting and negotiating. They discover, oh, I've got another modem I can talk to, and then the modem The modem negotiates a speed that they can both understand with integrity, with reliability, and sometimes that's faster, sometimes that's slower, depending on the quality of the phone line. To this day, the term modem has been carried forward when we talk about cable routers that connect internet broadband customers for companies like Via to the internet. And a cable modem, right, has the same function, performs the same function, and there's a DSP chip and there's a processor inside there, and it embeds that signal. So there you have it. When we talk about AM radio, that stands for amplitude modulation. So the waves are modulated over the carrier wave, and that's why they vary like they do. Frequency modulation means whenever there's a peak, there's more cycles or hertz, there's a pulse, right, of greater waves. And depending on the frequency of that modulation, that creates a distinctly active zone that we would interpret as a 1 or a 0, right? So that would be a 0, that would be a 1. I'm oversimplifying here, but essentially. Now, there is one other fascinating aspect of this, and this is where we're going to flip this on its side, and I'm going to plant a seed with you that I hope you'll take home. But there is a fascinating area of research where we put data on signals over electric lines. It's called data over mains. There was a trial project about 20 years ago to light up an entire subdivision in Britain and in Canada so that their electrical lines leading into each house in the subdivision, right, would carry their internet, their telephone, and their electric all in one, just on the one big electrical cable. And it was a success to a certain degree. But then there were other logistical challenges, and internet service providers had already moved very quickly. So power companies suddenly realized, you know what, it's going to cost a lot of money to compete against an internet service provider. And that never really reached fruition, except for the same concept on a smaller scale. It's called power line communications. And what are we talking about? This, to me, is really cool. You can take advantage, if you have a breaker box in your house, you can, and let's say gigabit, okay? So we're gonna do this. You can buy this in Office Max today. It's sitting on the shelf in Office Max. Can everybody see my screen?
Yeah.
So this is literally, yeah. So this is literally the same model that's sitting in Office Max on St. Thomas and St. Croix. I have a pair of these in my jump kit, right? So I have a jump kit with all sorts of data tools and such. There are different brands, Netgear, right? Makes some, D-Link makes them, TP-Link. But you notice there's an electric plug back here. You plug it into your wall, and it takes advantage of the signal noise, the electric noise in your wire, and it embeds, it modulates a data signal into the electric signal that's in your household outlets, back to your breaker box. As long as each one of these adapters is connected to an outlet that is served by the same breaker box, then you can establish a 1 gig connection to distant parts of your house where, well, let's just say the Wi-Fi signal isn't the greatest. So you have a main Wi-Fi router, you connect the main Wi-Fi router into this gadget, then you take a less expensive Wi-Fi router or just a wireless access point or a wireless extender, which is less expensive. And in the distant part of your house, you plug this baby into the other outlet in the dead zone of your house. You plug the other Wi-Fi extender or wireless access point or a cheaper Wi-Fi router into there, and then you configure the second router to be an extension of the first. And that is one quick way where you can cover every corner of your house. You can get multiples of these and you can set them to the same channel. So you can, now there are different channels and usually they're numbered or lettered, like channel A, channel B. Get the same brand, the same modules, you can all set them to channel A or channel B. Now there is an exception. If you happen to have solar power and you're off grid and your breaker box has noise filters, some noise filters will squelch the signal on the electric wire to the extent that the wireline adapter doesn't perform very well. But I've used these, and this is one quick way, you know. Now, how much do these cost, right? So let's go back and let's say Office Max, right? Last time I checked, gigabit wireline adapter, Office Depot. So you can get them in pairs in a kit. If you get them from Amazon, they're cheaper. But basically, you know, 50, 75 bucks. You're not punching holes in concrete walls. You're not trying to buy 2 more $300 Wi-Fi routers and trying to create a mesh network. That's just nuts, right? Cable is the way to go. So everybody's all about wireless, Wi-Fi, this and that. But sometimes the plainest remedies are so inexpensive compared to the, you know, the other options. And that's just something that I would encourage you to consider. If you would like, when I'm over on St. Thomas or on St. Croix, if you would like, we can Zoom. You can walk around your house and show me videos of what you got and how you got, and I will serve as your internet performance engineer, and we can spec out something you can try. And yeah, I've never had a complaint. In fact, once it's set up, everybody's happy. Everybody's just, why didn't we do this? Why didn't we do this? I wish I had known this 5 years ago. This has been around quite a while. Are there any questions about wireline adapters and how they blend the best of both worlds?
But if you know, a higher frequency, I mean, if the Wi-Fi is going at a higher frequency, how does the I guess the adapter pick up that signal if it has to move through some sort of physical object?
That's a great question. So the Wi-Fi signal is irrelevant because you're taking a short jumper from the Wi-Fi router. You're connecting Ethernet from the Wi-Fi router into the bottom of this thing after it's plugged into the electric outlet. Then,
Right. Okay.
and that converts the electric wire into an Ethernet cable, essentially. Then on the other side of the house, the other adapter picks up the signal and goes, oh, I've got some data here. And it hands off the data signal to the Ethernet cord, which feeds the other Wi-Fi unit. Now, when those two Wi-Fi units are connected through a cable, you can configure them so that they work together in tandem. And they're not doing it through the Wi-Fi signal. They're doing it across a hard cable. So, does that answer your question?
Yeah, yeah.
Yeah, it's really cool. Works really well.
And
Go ahead.
okay, so in regards to what is it? I guess electromagnetic radiation, right? So noise that interferes with a signal. How are we like? I guess as technology advances and they make, you know, better advances with I don't know if the word would be metallurgy, but they get better types of metal, would that end up diminishing that signal noise or that electromagnetic radiation that would interfere with the signal?
The short answer is yes and no, and it depends a lot on the circumstances. And I know that's not a simple answer, but I will tell you this. Newer versions of Wi-Fi and even the older version, the traditional G wireless and N wireless, you can set your Wi-Fi router to specific channels, and these are like sub-frequencies. And it's a well-known fact that if you set a Wi-Fi channel to 1, 6, and 14 in a tight area, those Wi-Fi routers will talk nice to all of the connected clients, but because they're on different channels, they won't interfere with each other and they won't jam each other. If they're all on the same channel and you put them close together, you actually step on the signal and jam. It's the reverse effect. So people get really frustrated. They're like, oh, I bought this extra router and it's just not working. And it's because they're all set. That's why they kind of need to be set up as a mesh, or they need to be connected with a cable, because the automatic configuration wizard that you can walk through says, oh, wait a minute, I got another one in the area. Let's set this one to 1. Let's set this one to channel 6. We'll set the other one to channel 14. And then those areas of overlap occur, right? So you get adjacent channels, and if they're far enough apart, 1, 6, and 11, or 1, 6, and 14, maybe it's 1, 8, and 14. There's several combinations that are particularly compatible. And that's one way to resolve a lot of interference between Wi-Fi signals in the area. And what we're finding is that a lot of Wi-Fi challenges are originating from too much Wi-Fi in the general vicinity and not so much other physical influences, okay? Now, you still have cases where everyone here has gone at one point in their life or another and had an X-ray in a hospital, right?
Yeah.
Yep.
Yeah, when you fire up that X-ray machine, it draws like 100 amps, and the electromagnetic pulse blacks out any Wi-Fi. So oftentimes X-ray rooms, radiology departments are shielded because, well, it just sort of steps on everything else. So there are cases where there are natural sources of intense radiation, electromagnetic radiation, because of the vast amount of current that's drawn. If you have high voltage power lines near you, that can step on your signals. And so those are things that, you know, you kind of have to keep an eye out for. So that's a good question to ask. And anytime you have consistent problems, or you go to the store, you buy a brand new Wi-Fi router and it's not much better. Well, that's your first clue that there's something else in the mix. And it's probably signal or physical. I hope that helps answer your question.
Oh yeah, no, yeah, it definitely does.
I have a question.
So yes, go ahead. You had a question also?
For like the gigabit, yeah, I had a question.
Uh-huh.
For like the gigabits, that you plug into the outlet,
Yes.
are those only for like or Ethernet cord as well? For like,
Are those only for like Ethernet cords? Is that your question?
yeah, because let's say if you have like a short Ethernet cord and it can't like go straight to your router, you could probably use those instead.
Yes, you could use those instead without stringing a long Ethernet cord. Exactly. That's a great question. So you can always string a longer Ethernet cord between point A and point B, but a lot of times the family dynamic doesn't allow for it. And that is one quick solution where everybody's happy. Usually it depends on the environment. there are ways to run a longer cable and to a point. And you know, it's a combination of things. You run a longer cable to get around one obstacle, and you put it in a raceway. You don't even know it's there. It just blends in with your baseboard or up by the molding, the crown molding, and you're at the top of your wall. But this is a specialty area where if some enterprising young alumni from UVI took this to task, you could become like the one-stop shop for anybody who wants blazing Wi-Fi in any environment, right? And it would not take very long to master the skill set, and you would be in demand constantly because of the, I mean, I'm getting requests all the time, you know. And at this point, I've limited it to the friends and family circle, and I do it for like rum cake or, you know, buy me a beer kind of thing. And I do one a month. I limit it to one a month because I'd like to stay married. You know, those kinds of things are an issue. Did that answer your question?
Yeah.
Okay. Now, we talked about modulation, and it gets better. There's another method of data transmission where, okay, the modulation carries the shared medium. So modulation is happening over the medium. It's happening over the wire. It's happening over the fiber. It's happening over the radio waves, right? And there's another way of increasing the bandwidth for that transmission from point A to point B. And it's called multiplexing. And I hinted at it already. I said, okay, Wi-Fi has channels 1, 6, 11, or 1, 9, and 14, something like that. And here you see sender 1, receiver 1, sender 2, receiver 2, sender 3, 4, 5, 6, all the way to sender N, receiver 3, 4, 5, 6, all the way to receiver N. And what we're doing is splitting the digital signal into different channels. That's called multiplexing. And that's often, that can be overlaid on top of modulation. This is where it gets a little confusing because people, it's important to understand AM, FM radio, that's modulation. Overlaying a signal wave on top of a carrier wave, that's modulation. But multiplexing is when you take that signal wave and now you take the signal wave and you put it on steroids, so to speak. You create subchannels or subfrequencies to create distinct pathways between a sender and receiver. So what's the net effect? You can support many more users on a single cable or a single media than you otherwise would be able to support. So what am I saying? The modulation does one part of this, the multiplexing takes it across the finish line, right? So that essentially a single form of media can support many more customers. And again, that's called multiplexing. Now, this is where some other familiar terms start to come into the mix. So radio and TV channels use FDM. That's a specific kind of multiplexing. Everybody knows we have different channels in radio and TV, right? So you're probably wondering, how do they do that? That's how they do that. WDM is used for light colors, right? That's in laser. TDM and CDM is used for, so TDM is used for phone and Ethernet. CDM is used for, no, cellular. Yeah, the C stands for cellular, right? Cellular. And yeah, those are important things to understand. Now, CDM is used for cellular service providers since it provides lower delays in service when the network is busy. Now, it was discovered that nonlinear encoding methods work better for voice, and that's called a mu law. It's used in North America and Japan. The A law is used in Europe. So there are different standards, which is why, you know, you have these smartphones and they're capable in some regions of the world, but not in all regions of the world. But then you have the really expensive smartphones and they work everywhere. This stuff is built in. So it has mu law, CDM type, and then it's also, it has the capacity for A law. So when somebody is in Europe, their modulation and multiplexing goes on without a hitch. And those are important distinctions. The slides from 290 to 300 in student notes, the publisher provided material provides that information. Now, I'm going to cover one more thing very quickly. You can also organize transmission types besides the method of transmission. You can organize transmission types by whether they are parallel or serial transmissions. Now, when we say parallel, we're saying that the media there is a media path for each series of ones and zeros. So if you have an 8-bit processor and 8-bit memory, there are 8 wires. Let me say that again. If you have an 8-bit processor and an 8-bit memory chip, and you have an 8-bit Wi-Fi card, really old computer, then you have 8 wires all in parallel next to each other, like a ribbon cable, okay? Here's what we mean. Now, in terms of data communications inside a system, when you connect an old school hard drive to the disk controller on an old motherboard, the conductor is actually a whole series of 16, 32, 64 bits wires, 16 wires, 32 wires, 64 wires, and they're all molded together, but they're separated by plastic. So there are 32 separate wires here, 32 separate wires. That's called parallel ATA disk. That's a parallel ATA or PATA data connection to I mean, at this point, really old hard drives. Now you also have SATA cables. SATA cables have one conductor, and the ones and zeros go really fast, but one after another. So we don't have separate streams of ones and zeros. We have one stream that's transmitted 32 times faster. Now let's say that. Let's say that again. Here we have 32 streams of ones and zeros all flowing nicely, but not very fast. Here we have one conductor that takes ones and zeros, 32 sets of them, and pushes them really fast in the same time frame. That's called serial communication, okay? Everybody understand what I'm talking about?
Yeah.
So single conductor, serial. Many conductors woven together side by side, parallel. They used to have printer cables that were parallel printer cables. And they had a Centronics end, and it was really blocky kind of thing, and they were very expensive. A lot of copper. And then all of a sudden, copper became very expensive. And then like crackheads would steal the printer cables for the copper because they'd get enough money if they stole enough printer cables. It's a long story, but it's the truth. They would get enough money for a fix. And then, well, let's just face it. If you're trying to be economically and ecologically sound, which would you rather do? Use like 32 times the amount of copper to do something, or 1/32 the amount of copper to move some ones and zeros? Doesn't take long to figure that out, right? Now, CPU and memory modules may use 64-bit parallel transmission. When you look at a motherboard, you see the traces, and there are hugely parallel connectors, and that's for digital communications between the components inside a system. serial transmission methods, now parallel transmission methods don't tend, I'm going to say this again, they do not tend to happen between systems, whole systems themselves. Usually it's serial transmission methods that occur between systems rather than within systems. And again, over time, everybody realized, hey, why are we doing so many wires inside the system? Let's do more serial stuff inside the box as well. So now serial transmission is really a very prominent method or type of data transmission when we're talking about signals. And what we're going to do is stop right here. And on Monday, we're going to pick up the bits, bytes, bauds, and other cool stuff on Monday. Given the information that's been shared, can anyone think of any interesting questions, or do you have any comments to share about the material presented? I hope you all have a great weekend. We're going to blitz the rest of this material on Monday and Wednesday, and then we want you to log your first attempt at the Module 2 assessment by the end of next week. We'll also put out the final version of the Module 1 assessment over the weekend, so that while the Module 1 material is still fresh, you can take that reconciliation and finish strong. Any questions before we break for the weekend?